I have not been the same since we had lunch. You explained to me, and I've said it here, the fabric of space-time might be woven by wormholes that connect the virtual particle pairs that come in and out of existence.
So it's like a little quantum net holding the whole universe together.
Exactly right. We find mathematically, if we cut the threads of quantum entanglement, space falls apart. It discretizes into little tiny pieces and then just disappears.
I gotta go. I gotta go.
This is StarTalk. Neil deGrasse Tyson, you're a personal astrophysicist. I got Chuck Nice with me. Chuck, baby.
What's up, Neil?
All right, all right. You know what we're going to talk about today?
I do not.
The only way to talk about physics is to talk about physics with Brian Greene in the house.
True. That is true.
Thank you.
You got to, you can't, it's empty unless you have Brian Greene in the conversation.
Absolutely.
And he's just up the street, up at Columbia. You're a dual professor of physics and professor of mathematics.
That's right. That's
wow.
right.
Do you get paid twice for that?
But I go to no faculty meetings. I'm always in the other department.
That's pretty cool. Yeah, I'm sorry, I can't. I'm math today.
So you're author of several books, Until the End of Time. Was that your more recent
That's
one?
my most recent,
And
yes.
that came out how long ago?
2020, right at the pandemic.
Right
what
at
a
the
moment to have a book called Until the End of Time, right?
Yeah.
And the one I think most people know, if they know you at all, The Elegant Universe. There's another one, The Fabric of the Cosmos.
Yeah, absolutely.
Nice.
That was the next one.
Hidden Reality.
Yeah, that was about multiple universes.
Right.
Man, so he's all up in
Right.
it.
I believe the fabric of the universe is a tweed.
A tweed. A satin weave.
A satin weave.
So welcome back to the show. This
Thank
is like you're more than a three-peat, I think, at this point.
Yeah.
Oh, God.
And you're involved in a lot of things. You're writing the book, other than being professor, you're writing the books. And are we in the 15th year of your World Science Festival? How many years have you been doing this?
That's right. We started 2008. So if you just subtract, it's even a little bit more. But the pandemic changed things a little bit. Yeah. But we're coming up to probably the 15th live event.
Congratulations on that.
you.
Although it's a little audacious to hold it in New York and call it the World Science Festival.
But we don't only have it in New York. We also have it in Australia. And we've had events in Amsterdam, in Moscow,
I got nothing. I can't.
in Italy, in Spain.
I know.
I try to.
Yeah.
And by the way, New York is the world.
Yeah.
Let's be honest. I mean, for anybody out there listening, I'm sorry. You go to Paris, you find Parisians. You know, you go to England, you find the Brits. But you come to New York, you find everybody.
Audacious would have been like the Cosmic Science Festival. Then you would have had a point.
Well, congratulations on bringing it to the world.
Thank you.
Or taking it to the world. And what I enjoyed most about the several that I've attended is the effort to bring the arts into it in a meaningful way.
Yeah.
Oh,
there are many artists who I would later learn are not rare, who are inspired by science and the universe and discoveries. And they will compose dance and music. And you have a mixture of these sessions.
We do. I mean, the goal is to have science feel connected to everything that matters to us. And of course, culture is a big part of it.
Culture and arts matter to everybody.
In fact, now with AI, we're doing a program on the arts in the age of artificial intelligence. So how is AI changing how artists approach their work and how scientists think about art?
There'll be more unemployed artists.
well,
but it's a funny thing. People say
just not paid. They won't be unemployed. They just won't be paid.
Yeah, but whenever new technology comes along, like the camera, people are like, okay, now you don't need artists anymore because anyone can just click. But there are artists who use the camera to create things that mere mortals can't.
And there are painters who actually take a picture and then they actually paint the picture as opposed to having someone sit for a portrait.
But that wasn't the biggest issue. The biggest thing, the biggest force operating was you no longer needed the artist to portray reality because, of course, the camera captured that. So that freed them up, freed the artist.
Yeah, that's right.
To portray impressionistic
beyond reality.
Yeah.
Exactly.
Yeah. It's not what the scene looks like. It's what the scene
feels like.
It's the interpretation.
That matters.
And it's huge. I mean, that's what is the magic in so much expression, right? It's what we do with it as opposed to just literally depicting what's out there. So there are many people who project that AI is going to create, a new kind of art.
Yeah.
Just the way the camera did.
Just the way the camera did. So it has to shake out. I still need to see.
I think AI it just accelerates creativity. It doesn't replace it, because what happens is you have associations that are being made at a level that you as a human being would maybe eventually, over a course of years, you might make those associations, but the computer can do it almost instantaneously.
Right.
And then you take that and you say, what does that mean to me?
Okay, so it pushes you along.
Yeah, but the flip side of that is if you have a computer creating so much, there's a lot of chaff, that you have to separate out.
That's so true.
So, yeah.
There's chaff even when people do.
Yeah.
You're born and raised in New York City.
Yeah, across the street from where we are sitting right now.
You went to Stuyvesant High School, which is a selective high school that specialized in science, in the way the Bronx High School of Science specialized. In fact, they're rivals. They're intellectual rivals.
Why do you think that we've wrestled each other now and then? I always lose, though.
You would not like a book if it didn't have equations in it.
It's true. That's true.
This is weird.
Yeah, that has changed, I should say. But
so you read a novel.
That's right, now and then.
That meant you thought more deeply about math than you thought about words.
Yeah, but the one change I would make to that statement was, it was when it came to books for a science class. If the book was chock full of words, I'd feel like, oh no, there's a lot of interpretation that's going to go into this particular science class. But if it was chock full of equations, I was like, nah, this is rigorous. This is going to be specific, and it's going to be something that I can nail, because I don't have to interpret. I can just really engage with the equations.
Wow. So in a history class or a literature class, you would have been in tears.
Well,
for the
again,
tasks
it was
required of you.
But it was just for science.
It was mostly just for science. But you're absolutely right. There is a different mindset that you bring to a history class or an English class, which I did not have a full appreciation for when I was younger. That's absolutely true. And as I got older, and especially there's a moment when I graduated college, and I said to myself, I think I just got a technical education as opposed to learning about the world and life and humanity. And I went into kind of a tailspin for a little while, because I was like, what did I do? And that really then changed it all for me. And words have become vital to the way I engage with the world.
You think? I mean, given his 4 best-selling books, but words matter.
That'll do it.
If you want to talk to other people who are not physicists.
And if you want to really get the essence of what someone's about, as opposed to quantifying some quality of abstract or objective reality.
Okay. Yeah. All right. I think that's an enlightened posture.
Yeah. I've gotten there. Yeah. Took me a while.
So what I want to do is follow up. There was a question to our cosmic queries that I didn't have an answer to.
Oh no, here we go.
Okay. Yeah. And I said, I don't know. I got to.
We're going to have to get Brian Greene in here.
You got to get the big guns in here. All right. If I remember the question, it was, what happens if a quark falls into a black hole? You have a quark pair.
Yes.
And we've only ever found them in quark pairs.
Yeah.
Okay. And in a normal lab, if you take them and pull them apart, the force that wants to bring them together grows, which sounds weird when you're used to gravity and other things where distance makes something weaker.
But they're like really creepy identical twins. Like, you ever meet identical twins that are like super creepy?
Where they sort of
talk together, and they got their own language. Yeah, and they right.
So, but it's kind of like a rubber band.
Yeah.
Because you stretch a rubber band, the force is greater.
Yeah, the gluonic force between them.
The gluonic force, because it's held together by gluons. Okay, so now, as I pull it apart, there will be a point where it snaps. As I understand my nuclear physics, it snaps with the exact amount of energy you put in, so that out of that energy creates 2 other quarks.
Yeah.
So now I have 4 quarks.
Quark-antiquark pairs produced.
Pairs, so thank you.
Yes.
Okay, pairs. Yeah. Okay, so now.
So you want to see what happens.
Now you send a pair of quarks down the black hole, it gets split, we make 2 other quarks.
Yeah.
Thank you. That was very good. And you keep doing this, and so wouldn't the quarks eat the entire gravitational field of the black hole?
Yeah.
And that you wouldn't have a black hole left, you just have a ball of quarks.
You have to realize, number one, that we still don't know the physics of the singularity of a black hole well enough.
Why else did I invite you into this office now?
Well, I wish one day, I pray that I'll sit here and tell you what happens at the singularity of a black hole.
Bring the person who knows next time.
But here's the thing. There is nobody on planet Earth who knows the answer, unfortunately, yet.
Okay.
When we follow the mathematics to the actual singularity of a black hole.
Using Einstein general relativity.
Using Einstein general relativity, and even some of the modifications that have come from more recent thinking, we're still not there yet to truly understand what happens. But I should say there are ideas. There are ideas of things, I don't know if you've heard of them, called fuzzballs, where there isn't actually a singularity, and the black hole is actually a more fuzzy collection of matter. So there are ideas that people
that makes your math come out okay.
Makes the math come out okay, but
because
we're not sure if it's right.
What they say, the black holes are where the singularity at the center of a black hole is where God is dividing by zero.
Yeah, that's a Stephen Hawking quip or something. Say that? I think it is.
So
you know,
you remember why if you divide by zero,
it's not going to work out, right?
Yeah, and it's actually, in a sense, it's literal, because if you calculate what's known as the scalar curvature, which is a number that characterizes how warped a region of space is, it does go to infinity as you go to the center of a black hole. Just like when you divide by zero, it goes to infinity. In fact, it goes to infinity as the 6th power of your distance. So we know very well how badly behaved the center of a black hole is.
So it goes to infinity fast.
It goes to infinity fast.
That's crazy.
Yeah. And so if you ask what really happens if something is just being crushed at the center, we can't really answer yet. So is it possible that as a quark-antiquark pair goes, that the tidal forces will create additional quark-antiquark pairs? Sure.
And then you'd have the proliferation of quarks. Give me some sounds.
Yeah.
Right.
So there may be a cloud, and there may be some sort of cloud that forms just before it hits. Ultimately, we believe it hits the singularity, whatever that means, because we don't really know what the singularity is.
If it's a fuzzball, you can have a fuzzball of quarks. Possibly.
Or the fuzzball may have a slightly different impact on the quark-antiquark pair. Maybe before influence on it. Yeah.
Impact.
That's right. Exactly. Yeah. So it's a really good question, but it will have to fully await a full understanding of what truly happens.
So me
at the
not being
center.
able to answer it wasn't just my personal ignorance. It's a total ignorance of all humans on Earth.
Yeah, and
so I don't feel so bad.
And I should say there are many, many questions like that we're still struggling with. Like, we believe that when any information falls into a black hole, we believe that information does not get destroyed. But for a while, Stephen Hawking thought, no, any information ultimately hits the singularity and leaves our universe. He changed his mind later in life, which just goes to show—
Was that his famous bet with Kip Thorne?
That's right. So they bet, I think, an encyclopedia, the source of information that we humans have created. So
Kip Thorne was one of the executive producers on Interstellar. And he sort of spearheaded the effort, among others, but he was the exponent to build the laser interferometry gravitational wave observatory, LIGO, that detected colliding black holes, and he won the Nobel Prize for that.
Yeah.
So he's significant in our field, and I have at least a few books by him on my shelves. Yeah.
And he was clearly on a level of geekdom where he bets encyclopedias.
But in terms of his book, he wrote an encyclopedic book on gravity and black holes, which is about 1,200 pages just filled with equations. Therefore, I loved it when I was a kid.
Wait, with the Misner-Thorne-Wheeler?
Yes.
I have 2 copies of that in my office.
2 copies?
Yes.
You want to cross-reference or something?
To make sure
one of them is mine, and the other one belonged to my wife. I was a PhD in mathematical physics.
That's so cool.
We met in relativity class.
Really?
Taught by John Wheeler.
What? Really?
Yes.
You took relativity from Wheeler?
Yes, I did.
That is amazing. Wow.
Yeah.
Nice.
Yeah. So John Wheeler is one of the authors of this Misner, Thorne, and Wheeler.
Yeah.
And Misner taught physics at University of Maryland.
Charles Misner.
Charles Misner. Yeah. Okay. So I would think of it as a quark catastrophe that would happen in the center of the black hole.
The trouble with quarks. They're like tribbles.
By the way, there's a previous, if we're physics geeking out here, there's a previous time, was it 110 years ago, where there's something called the ultraviolet catastrophe. Yeah. Do you remember that?
I remember it. Well, I wasn't there, but I've learned about it. Yeah, this is the start of quantum physics.
Yeah, it predate 1900.
Right.
It predated Planck, Max Planck.
Oh, okay.
Because there was an equation that would show how much energy would come from glowing objects.
Okay.
And how much energy of a certain wavelength of light and then another wavelength. And so there'd be the spectrum of what it gives you.
Okay.
And if you follow that equation to higher and higher energies, it blows up. And it was called the ultraviolet catastrophe.
Nice.
Now, we knew that's not happening in the actual universe,
Right.
but we had no theoretical understanding of why the actual universe was not doing what our equation said. So we knew something was missing.
Okay.
And
What was missing?
Max Planck comes along, finish the story.
Yes, and Max Planck comes along and he suggests an idea that he never fully believed. This is interesting. He suggests that maybe the energy only comes in packets of certain quantized sizes, and therefore your calculation of the amount of energy was biased by assuming that energy could come in arbitrarily large or small amounts. If you assume it only comes in packets of a minimum size, then the total energy inside that cavity
It actually
is
converges
finite.
and drops off.
And it agrees with experiments.
Right.
But the weird thing is,
And he got an equation. The equation is like, holy shit, that this would come out of someone's head
Yeah.
Right.
to make this happen.
Yeah.
It's got an exponential, and an exponential has interesting properties where it goes up and then it comes down again if it's a negative exponent. I mean, there's a fun math in there.
Exactly.
And was it just a fitting function, or did he actually have deep physics insight? do
he
you
had a
think?
model in mind. He really quantized the energy. He broke it up into little bits and redid the calculation, and that's what came out. But then later on, he never fully believed that energy in light, in photons, as we now call it, did come in little packets.
Right.
He said, sure, the math seems to describe it, but I'm not willing to go to that next
not all
step
in.
of ascribing a full reality to it. And so it's really Einstein who came along and came up with the idea of photons, more particularly with the photoelectric effect. And that's how he wins the Nobel Prize.
Yeah.
Many people think he won the prize for special relativity or general relativity. No.
My boy could have had 8 Nobel Prizes. His Nobel Prizes are for what he's least famous for.
Right. Yeah.
Right. I mean,
but perhaps
That
the most
just means you're
impactful.
gangster. That's straight up.
Yeah.
You know?
But in
the
terms of
crumbs that
impact,
spilled
Right,
off his-
exactly.
There
Yeah.
are people winning Nobel Prizes for discovering things that he predicted.
Right.
So if you add everything he predicted to the Nobel Prize count, plus what everything, if they gave out Nobel Prizes for everything you did, I give him 8 Nobel Prizes. What would you give him?
well, certainly gravitational waves, although
That's
again,
right, which we
he
just-
didn't fully believe it, but it comes right out of his 1916 and
I'm
1918
saying if you
paper.
give him a Nobel Prize for everything people discovered based on his stuff,
Well, then it's kind of everything. I think.
person's on the Nobel Prize receiving line said, nope, take it.
Right. It's like that Bugs Bunny first base, Bugs Bunny second base, Bugs Bunny third base. Every Nobel Prize
You're right.
is Albert Einstein.
That's the answer right there.
Yeah.
And so, of course, since if energy is quantized, thus is born the branch of physics called
Quantum
physics.
mechanics.
Quantum
Yeah.
mechanics.
Wow.
Yeah.
And that probably has had the greatest impact on life as we know
And that was
it.
the year 1900.
Yeah. Well, 1905 is when Einstein writes his paper on the idea of photons. But Max Planck, you're
Max
right, was
Planck
1900.
was clean
Absolutely,
1900, starting a new century.
Yeah.
Before they even had calculators.
Oh, was that? Really? Was it that far back?
As you may know, we recently posted a video in response to Terence Howard's appearance on Joe Rogan's podcast where he discussed his interpretation of maths. And key points to take away from that are 1, we should critically analyze all the information we come across, and 2, be open to our views being challenged. Like this new study on dark matter being debunked, for example. It suggests the universe's expansion is not driven by dark energy, but by weakening forces of nature. Now, when it comes to new theories that challenge our accepted understanding of space, it's important to see how different scientific sources are interpreting these new findings to fully understand it. Luckily, ground news makes this much easier to do. With the Vantage Plan, you get access to original research, plus every article covering it and even insight on each news publication's political bias and credibility. Context that could influence their reporting. Their founder and former NASA engineer also designed their blind spot feed, which uses patented technology to help us easily step out of our echo chambers and see important news stories we might have otherwise missed. Exposing yourself to diverse perspectives helps ensure that you don't just know enough about an issue to think you're right, but you actually know enough to recognize when you might be wrong. So, avoid the Dunning-Kruger effect, get ground news, and critically analyze the information you consume. All for $5 a month if you use our link or scan the QR code. You're saving 40% on the same unlimited access Vantage plan you use with the discount. We really can't recommend Ground News and their commitment to rigorous analysis and combating misinformation enough. Having said all of that, let's get straight back to the show.
We're old enough to remember when the United States lost the most powerful collider in the world, this superconducting super collider, which there was money allocated. They started digging a hole. What was it, 200-mile circumference or something huge, and superconducting, it was going to use superconducting magnets, which had very powerful magnetic fields. And because that was coming of age at the time, it was going to push the frontier. My analysis, if you read the report, well, there were cost overruns and so we have too many other priorities here. So we're going to zero the budget for this superconducting super collider. And you read the report and say, well, we have other priorities. Plus, this was going to be built in Texas. And if we're going to build the space station, which is based in Houston, Texas was already getting a chunk of change. You know when all this happened? Like between 1989 and 1992, when the debates and then they zeroed the budget. What else was happening over those years? Let me think. Oh my gosh. Peace broke out in Europe. No longer do we need the physicists to protect us from the evil, godless communists. That's what I think was the subtext of that story.
Damn you, Harmony.
Because no other particle accelerator was ever canceled for any reason that was designed, conceived, and built in the 20th century. So if you grant me one conspiracy theory, grant me that.
But then you think they kept the space station because that was the place where the new battles might be waged? I mean,
possibly.
Makes sense. It's what we're looking at right now when you think about it.
Yeah, with the Space Force and everything else. So that's where I am on that. But I say this only to note that once that got canceled, the center of mass of particle physics went across the pond to Europe. And then CERN, the European
Center of Nuclear Physics.
Nuclear Research?
Somewhere in there, yes.
It's a French acronym when the words are in the French order or something.
Gotcha.
It goes there. And I think our lawmakers don't really understand that if we don't do the physics, someone else can and will. We don't own all access to future discoveries of science. And so now Europe does it. And so they went ahead, built a large Hadron Collider, and they successfully found the Higgs boson, the big holy grail.
July 4th, 2012.
Look at that.
Was it July 4th? That's sticking it to us.
Wow,
Look at that.
It really was.
And you know they really found it on like June 28th. You know they found it on June 28th, and they were like, guys, we're going to sit on this for a few days.
But there are a lot of Americans involved in the Large Hadron Collider. But just to say, but yes, exactly right.
Yeah, even Peter Higgs, is he American?
Peter Higgs was Scottish, I would think. I think he's from Edinburgh. Although I think he was at Edinburgh, but I don't think he was Scottish. Maybe he was English. I don't 100% know. But yeah, he predicted its existence, and then it was discovered. And at the announcement, saw tears welling in this man's eyes, who'd been waiting decades for this idea that at first nobody believed. Ultimately was accepted theoretically, but it was proven experimentally finally.
And what is the Higgs boson exactly?
Of the particle categories, one of them is bosons. Okay. And bosons are force mitigating particles.
Okay.
So, and when we think of a force action at a distance, there's a way to think about that in terms of the particle that in the category of particles is a boson. One of the bosons is this Higgs boson, which has what properties?
Well, it has.
Was I right?
Yes, very good.
Thank you.
Yes,
thank you. We said I was very good.
Can I answer?
Thank you, Brian.
Please.
Okay.
It's what endows other particles, even itself, actually, with mass.
Interesting.
Now, where does that come from? Well, just to take Neil's idea, it starts with the idea of a field. That's how you get rid of this idea of action at a distance. You imagine that space is filled with stuff.
You know who invented fields?
I really don't.
Michael Faraday.
Yeah.
Oh, really? Well, that makes sense.
He was the first
well,
to
they think
think
it
of
is-
Magnetic field.
And think what a leap that is.
Yeah, that
Huge.
is.
Yeah.
It's an
Right.
insane leap.
Right,
We
'cause
take
there's
it for
like nothing
granted. There's
there.
nothing
Right,
there.
yeah. You're looking
You
at
know.
nothing. You're seeing
And yet
nothing.
you're positing that there is something there.
something's there.
Yeah, and
Okay.
that's an amazing thing. But he was talking electric and magnetic fields.
Right.
What Higgs is talking about is a new field called the Higgs field, which he didn't call it that, but
Right.
that's what we call it. So it's this field that fills space, and as particles that otherwise would be massless, as they try to go through space, they have to burrow through the Higgs field.
Okay.
And that creates a kind of drag force on them, which is what imparts the mass that they have.
Okay.
And that's the field. Now, what's the particle? Well, if you have this field, in principle, if you hit it hard enough, like hitting the surface of water, you can cause little particles of the field to spray
Blast
out.
out, right.
And that's what the Large Hadron Collider did. It slammed proton against proton, and that way jostled the Higgs field and caused a little droplet of it to break free, and that's the
and
Higgs
then we
particle.
got the, oh my God. So you're seeing an actual piece of the field.
Yes.
You're, oh
Wait,
my
wait,
God.
so the Higgs field generated via E equals MC squared,
Yes.
Right.
its own particle of its own.
That's amazing.
That's right.
Of its own
the
DNA.
or you can say it's a quanta, to go back to the other language, it's a quanta of the Higgs field, like the photon is the quanta of the
of the
electromagnetic
electromagnetic
field. Yes.
All right. That's
Ain't
amazing.
that some stuff.
So
Okay, but
okay, now I get it. So it's not the particle that you're actually seeing. It's not the particle that is imbued with mass itself. It is the thing on which the particle is traveling, the field, the medium itself.
Right.
Boom, it kind of splashes apart for a quick second, and then that itself becomes a particle and has mass.
Yeah.
Holy
wait. So you know,
that's amazing!
wait. So you know,
That is amazing!
Chuck just blew a gasket.
Oh my God, that's crazy! Dude, that is insane!
Call the doctors.
This is the first time I've actually really understood
Call the doctors.
that because, oh my God, that's so freaking crazy! Oh my God!
A week later, he's there in bed still. Eyes this big.
That is fantastic.
So my favorite analog to this
Yeah.
is when I explain the Higgs field to people, I say it's like a Hollywood party.
Uh-huh.
Okay, so there are people in the party.
Right.
All right, and the bar is at the back of the wall.
Okay.
Okay, and if no one knows you and you walk into this party,
Okay, that's my experience.
you have near zero resistance to movement through that party.
True.
So you have a very low, if not zero, party mass.
Exactly.
Okay? Because you have no...
You
no,
get into the bar right away.
Right, you get in the bar right away.
Right
So
away.
your inertia, it knows no resistance there.
Exactly.
Whereas if Beyonce walks in,
Uh-huh.
everybody will crowd around here. She can only make very small steps towards the bar.
Right.
She has a very high party mass. Is that fair?
That's awesome.
it. That's the party field.
The party
And
field.
then if you slap all those party goers, you can slap off one of them. That's the party
Somebody
particle.
from the beehive. Somebody from the beehive pops out.
Yeah.
Oh my God, that's Beyonce. You're like, oh, there it is.
All right, so I learned, not from you, and I'm disappointed because I thought you would have told me the whole story.
Yes.
I come to you for these frontier conversations that the Higgs mass that a particle would have is only for free particles. If a particle
Yes.
is in an atom,
But I have,
it's not getting its mass
I
from the
have
Higgs
told
field.
you this in the past, though. I absolutely have.
I don't think he- I don't think-
But you're absolutely right. Absolutely right. So
if I'm a fat proton
yeah.
in a nucleus,
Yeah.
I'm not getting my mass from the Higgs field.
No, and that's why it's a really misleading notion that many people have. They think that all mass comes from the Higgs field. It is just the fundamental particles. And here's the thing, if you were to go up into your particle data book, which I know you have a few
do.
copies lying
Yes,
around
it's
in here.
particle data. It's very good.
If you look up the masses of the quarks, the up quark and the down quark that make up a proton, up, and a down, add up their masses.
He said that quickly.
Up,
it
and
has
the down.
The nucleons have
Right.
3 quarks
Right.
in them, all bound together, making up the proton and the neutron. But they're different combinations of 3 quarks. This is good. Tell them. So quarks have charges, fractional charges.
Yes.
Right? So watch this. Watch
Okay,
this.
go
So
ahead.
proton has a charge of +1.
All right.
How do you get that from 3 quarks?
Yeah, how do you do that?
So give it to me.
You got to have a 2/3 and a 2/3 and a minus 1/3.
2/3, 2/3 minus 1/3.
So 2/3 plus 2/3 is 1 1/3, and then a minus charge to bring it down to 1. Now, neutrons have charged quarks inside of them, but they don't have any charge. So how do you get them?
How you get them? Let's hear it.
Oh, it must be up 2/3 down, 1/3 down, 1/3.
Yeah, so if you have an up and then a down and down, then you got a 2/3 minus 1/3 minus 1/3.
Minus 1/3.
Now,
canceling out, and so as a neutral thing, even though what's inside of it has charges.
Right, but here's the thing. The point I want to make, though, is if you add up the masses of those quarks, they're much less than the mass of the proton. So what's going on here? They make up the proton, and yet the proton's much heavier than its ingredients.
Right.
Answer is there's another contribution to the mass, which has nothing to do with the Higgs field, which is the thing we were talking about before, the energy in the glue holding the quarks together.
Oh, the gluonic
There's
force.
energy holding them together equals mc squared. There's mass associated with that energy, and most of the mass of the proton is coming from the glue that's holding the quarks together.
That's insane.
So let's take a neutron, which has a half-life in minutes, like 15 minutes if memory serves. And after that amount of time, half the neutrons will have decayed into a proton, and let's say if it's a regular proton, and then an electron,
and an antineutrino.
And an antineutrino. If you add up the masses of those, don't you recover the mass of the proton?
As long as you're taking kinetic energy into account and all this too.
Because they fly away.
They fly away. But yes.
So the energy budget is all there.
Oh, it's all there.
Okay.
Look at that.
Well, okay.
So everything is conserved.
Yeah,
all the time.
And in fact, the way the neutrino was predicted was from looking at these particle decays and finding that the energy budget was not adding up. And so the idea was maybe there's an invisible particle that's carrying away some additional energy.
Was this Enrico Fermi?
Yes.
So what I like about this is he's like,
wild.
look, folks, I can't explain this. Let's make some shit up.
Yes. But geniuses make up shit that's right.
There's a quote. That's a quote. That's a bumper sticker right there.
That's it. I'm getting a t-shirt. I'm getting that t-shirt. That's awesome. That's great.
That's what Carl Sagan was famous for saying. They laughed at Einstein. They laughed at, all these people with these great ideas. And he said, they also laughed at Bozo the Clown. So, just because people laugh doesn't mean they're going to be wrong.
Right.
He makes it up, and then everyone starts looking for it, and it's this highly elusive particle that has no charge, because we knew all the charges had already balanced in the lab. It's got no charge, but it's carrying away energy, and no one has detected it. Right. And he was Italian, right? So neutrino is like little neutral.
Little neutron.
Little neutral one, I think is
that may be right. Little neutron.
Little neutral one.
Yeah, right.
And so that's the only thing that allows me to, okay, I'm not going to get in your way. When people saying dark matter, it's some elusive particle that we can't detect.
Right.
That's accounting for the extra gravity. And it's a particle, we haven't found the particle yet. And I'm thinking that's intellectually lazy, but it's no different
than the neutrino.
Than the neutrino. Yeah. So that's why I cut it some slack, more slack than I otherwise would.
Now, we still need to find it.
We still haven't found if it's a particle, we haven't found it.
Yeah, right.
So are you a betting man? Is it a particle or is it something else?
Look, I'm relatively conservative when it comes to these things, so I think that it's likely to be a particle. But
just because we've been down that road before.
We've been down that road before. It fits in so well to our theoretical framework. It doesn't require.
You have a slot for a dark matter particle?
Well, the amazing thing is, and here's where you're going to come back at me and say this should undercut my confidence. When you look at a theory called supersymmetry that I've spent a long time working on.
Okay.
Within this theory, which goes beyond what we know about particle physics for reasons that are well motivated.
Because that's ordinary symmetry.
That's right. It takes the symmetries that we have and it takes them one step further, and it's the only step further that you could possibly go. So of course nature must make use of this final symmetry principle. Why else would it exist? That's the thinking that we've had.
Right, just let me back up for a minute.
Okay. Yeah.
So as I was learning particle physics, I was intrigued to recognize that you have your electron, you have your photon, you have your neutrino, and these other sort of basic particles. And they exist in our world that we experience. Okay. If you up the energy knob, other particles manifest. There's a version of the electron that manifest only in these higher energy levels, and it's called a muon.
Right.
Okay? And so there's a whole layer of particles sitting above the ones that are in our world.
Right.
So there's 3 of these layers. And tell me the 3 electrons.
You get the electron, the muon, and the tau.
The tau.
Yeah.
Okay. And there's an electron neutrino, there's a muon neutrino, and there's a tau neutrino.
Yeah.
Right.
So now I have 3 layers here, and you have access to them in your particle accelerators because it takes a lot of energy, and you can get there.
Yeah.
Okay.
Right.
Now, what does supersymmetry do with this package?
Supersymmetry says
this package is
beautiful and confirmed.
and tell me the 3 force carriers. We have a photon.
You got the photon, then you got the gluons, and the W and Z bosons, or the weak nuclear force.
Okay.
And those are the
Discovered
3
by
forces.
Bozo.
Yeah.
Right.
Bozo.
Bozo.
Actually, Bose.
Yeah.
Bose is an Indian physicist.
And, yes, absolutely.
Yes.
And then for the quarks, you got the up and the down that we spoke about. You got the
Right.
charm, the strange. You got the top and the bottom.
Right.
So,
So you
again,
have
they come in 3 pairs of 2.
quarks.
Oh,
Yeah.
okay.
Yeah.
Okay.
Supersymmetry says take all of those particles and double them. Another shadow version of all of those
It's a
particles.
shadow government.
For the electron,
We are the puppets.
this is the deep state.
That's the deep
This is the deep state.
They are the puppet masters.
That's right.
The quantum deep state.
Yeah.
Wait. So I didn't know this. The entire set of particles
Yeah.
would have a counterpart in this supersymmetric
Yeah.
place.
So for the electron, you have the supersymmetric electron. For the quarks, you have squarks. For neutrinos, you have sneutrinos.
People just making shit
I
up.
know.
You know, you do
That's
run
it.
out of
Just
names
look at
after
the
a while.
latest cartoon. And
But here's the thing. This is all mathematically motivated by a completely compelling rationale. So this is not pulled out of, thin
Nowhere.
air.
Thin air.
we have our universe 3 ways, a 3-layer cake. And there's a whole other cake. Where does that live?
With us, but we believe they're more massive, which is why we wanted to build the superconducting super collider
wild.
to try to find them. Now we've looked for these at the Large
If
Hadron
they're more
Collider.
massive, why aren't they right here in front of our faces?
They typically have short lifetimes, so they'll decay into lighter particles. But the lightest of the supersymmetric particles would not decay, and therefore it should be all around us.
Tell them why the lightest one would not decay.
If it's the lightest one, when it decays, the decay products have to be lighter than it.
Okay.
And so if it's the lightest one,
Right.
subject to a certain
It's no place for it to
conservation
go.
law.
No place for it to go.
There's no place for it to go.
In
Yeah,
essence,
No place to go.
yes.
It's the same reason why you can have an energy field of any kind, and you will not make particles out of that
Right.
unless the energy available is higher than the E equals mc squared of 2 electrons,
Right.
because it has to make them in pairs.
Okay.
Am I
Keep
getting
the
it?
charge
To keep the
conserved.
charge-
Yeah,
conserved.
because it's plus and a
Yeah,
minus.
right.
And so an electron is the lightest physical particle. That's right.
Right.
So nothing's happening.
Lightest charge
That's why it's
particle.
not happening around us right now.
Yeah, it's the lightest
Right.
charge
It's charge
particle,
particle,
so
right.
it has to talk to the electromagnetic field. for
There it is.
instance.
That's why light coming from lights is not just making particles. It doesn't have enough energy.
Yeah.
Right.
But if
it did?
if X-rays started to come out of there, X-rays, high energy X-rays, you can pop electrons into existence.
Yeah.
Because they're stepping down, so they leave something.
The energy of the field is big enough to create the electron and anti-electron, and so it will pair produce them.
In fact,
That's so wild.
electron microscopes are enabled by X-rays creating them, and the wavelength of X-rays is so tiny that you can see tiny detail. It's tinier than the detail. You can't have resolution higher than the wavelength of light that you're using
you
to
can
see
use
it.
to see it.
Right.
Right.
Now, back to dark matter, just to finish
Right there.
this point.
So this is a whole massive other layer cake,
Yep.
and you're telling me that is the mass of the dark matter.
Well, the lightest supersymmetric particle would be stable, should be around us.
That's what
So
everybody's
maybe
looking
it's
for?
filling space.
Right.
And here's the beautiful thing. This will
So
blow
this
your mind. This will
actually
blow your
makes
mind.
sense.
This
My
will
mind's
blow your
already
mind.
blown.
When you do the calculation of how much of this lightest supersymmetric particle should be left over since the Big Bang, it exactly matches what you need to be the dark matter. It comes in the right abundance.
Dang.
And yet we've not found it.
You
And it
haven't
may
found
be
it.
the wrong answer. So sometimes things that just seem so deeply compelling are wrong, but we don't know yet.
Wow.
So do you know enough in the theory of these particles to predict how you should detect it?
Yes. Now they can vary which is the lightest supersymmetric particle on the flavor of the supersymmetry theory you're looking at. But in any given version, yes, you know exactly how the particle interacts.
Okay, so now you have everybody's favorite flavor, the theorists, come out with their competing models, but still they got to have one of these particles. Okay, so now I'm a experimentalist, and it's, let me test for this one. I don't find it. Let me test for that one. I don't find it. So it's not looking good.
Yeah, I agree.
Okay.
I agree.
Okay.
Wow.
I agree. But yeah, when I was a student, it was almost a foregone conclusion that you just had to look for it. You'd find it. This is the dark matter, because supersymmetry also solves other problems, the so-called hierarchy problem. It solved the dark matter problem. It's a beautiful idea that seems perhaps not to be right. Now, it's not fully ruled out yet, but that may be where we're going.
Who's the one that said the great tragedy in science, a beautiful theory, slain by some facts? Somebody said, I forgot. 100 years ago.
Exactly what it may be.
Hey, StarTalk fans, I don't know if you know this, but the audio version of the podcast actually posts a week in advance of the video version. And you can get that in Spotify and Apple Podcast and most other podcast outlets that are out there. Multiple ways to ingest all that is cosmic on StarTalk. I have not been the same since we had lunch months ago, and you explained to me, and I've said it here, that there are ideas percolating that the fabric of space-time might be woven by wormholes that connect the virtual particle pairs that come in and out of existence. And that if they're connected by wormholes, rather than just some field, then the wormhole is an actual structural texture of the universe.
Yeah. In fact, the other way.
Now I'm sorry.
What?
First of all, I need some weed to even deal with this. Because if I'm trying to figure out what you just said here, because it's so freaking, I mean, it really is just crazy.
Well, let's back up. The vacuum of space is not a vacuum.
Right.
Because quantum physics requires what?
There's all sorts of uncertainty, and that uncertainty means that there's fluctuations, and therefore there are particle-antiparticle pairs, there's energy fluctuations, there's field fluctuations.
Right.
It's a roiling mess out there in empty space.
So there's no nothing. There is no such thing as nothing.
That violates uncertainty if it was truly nothing.
Right. If it was truly nothing, we couldn't have uncertainty.
Yeah.
So the uncertainty is, gives us the fact that we do have virtual particles.
Yes.
We know that they pop in and out of existence. Well, what you're trying to tell me?
I think it's not that we know they're there. No one denies it because it's completely consistent.
Well, I'd say the Casimir force, where you actually put two metal plates in otherwise empty space, they should simply sit there. They're drawn together, and our best explanation is it's the virtual pairs of particles. It's the fluctuating field.
I did not. I feel like I have fallen into a Star Trek nightmare.
So you take two exactly parallel plates.
Okay,
and evacuate what's in between them.
That makes sense.
The best vacuum you can muster. Then you slowly move them together.
Right.
There is a point within which a whole other force kicks in.
That's right. And it's not the gravitational force.
It's not
the electromagnetic force. Rather, it's a force that comes from the Casimir field, which is basically...
That got a Nobel Prize, the Casimir?
1948 is when it was discovered.
Okay.
It got one in my book.
But it should have.
You just gave it one.
I just gave it one.
Yeah, it definitely deserved one.
That's insane.
But it's an imbalance between the fluctuations of uncertainty within the plates and the fluctuations of uncertainty outside of the plates.
Oh.
And it's that imbalance.
Creates a force and puts them together.
Yeah.
Okay. So that's how we get the particles in the vacuum of space. Okay. So now,
unbelievable.
So now, what compels you to say wormhole rather than just a field?
Right. Well, because it really comes from the idea of quantum entanglement. What we find is that entanglement, which normally we think of as particle pairs, but now we're finding that the vacuum of space may be stitched together by the threads of quantum entanglement itself. So deep down within the substrate of reality, it may all be stitched together by quantum entanglement. And then other work shows us that quantum entanglement connecting two particles is just like a wormhole, going from one to the other.
Because what happens in one happens to the other instantly.
Yes.
And that means they're touching each other in that instant.
They're connected in some weird way. And entanglement is one language, but we believe wormholes may be the general relativistic version of that quantum language.
So it's like a little quantum net holding the whole universe together.
Exactly right. Because we find mathematically, if we cut the threads of quantum entanglement, which we can do mathematically, space falls apart. It discretizes into little tiny pieces and then just disappears.
I gotta go. I gotta go.
No, Chuck. I need you to the end of this. Chuck,
Dude,
don't leave me. Don't leave me,
Oh
Chuck.
my God. Oh my God. Dude, that's insane.
It's not just that there's a field there. It's the fact that they were quantum entangled that makes the wormhole model compelling.
Yeah, but I would say you don't even need the particle pairs. It's as if the entanglement is entangling regions of space. So space itself has a fundamental substrate woven by these threads of quantum connection. Now look, it's mathematical, but it comes out of our cutting edge ideas. It all makes sense.
It just makes
He's
sense.
saying he's not pulling it out of his ass.
Right.
Okay, he's saying the math gave it to him.
Works.
And he started out saying my boy loves the math. So now, last thing.
Yeah.
Explain why you need more than 4 dimensions for your string theory universe.
Well, it's a very concrete explanation. When we look at the equations of string theory, there's a consistency equation where something must equal 0 or the math doesn't work. That something is a product of 2 things. One term is really complicated. It's never 0. The other term is the number of dimensions minus 10. The only way to get it to be equal to 0 is for D to be equal to 10. That's it. I am not joking. This is where the constraint of extra dimensions comes from in string theory.
The math is forcing our hands.
Forces your hand. And then you say, well, let me take this math seriously. One thing you could say is, well, if it's not D equals 4, 3 space and 1 time, throw the theory away. Others of us will say, hey, let's consider the possibility.
Don't sell the universe short.
Yeah, exactly. So why should these 3 dimensions of space be the only ones?
Right.
We only are aware of them because they're big enough that we can be directly aware of them with these really faulty sensors that we have.
Right. If it's only your senses that limit that awareness, why not, in principle, can we build something that can gain access to these higher dimensions?
Yeah, so there are experiments on the table. Some have been carried out, but more precise ones may be done where you study Newton's law of gravity. Why does Newton's law go like 1 over r squared? Why do we teach our kids GMM over r squared?
It's a geometric
sphere in 3 dimensions of space.
Yes.
Look at that sphere in 4 or 5 or 6 dimensions, and the 2 in Newton's law won't be a 2.
No.
It'll be a bigger number. The fall off will be differently.
Right.
And so look at the gravitational force on very small distances. Look for a deviation from the 1 over r squared that Isaac Newton told us about in the late 1600s.
Okay, because that's only in our dimensional measurement of it.
Yes.
Okay, because I'd asked you, again, over that same lunch.
Yeah.
Why did we have lunch? I forgot. We were just
We were
catching
hungry.
up. No. We were just catching up. You know, it's my annual fix, my annual Brian Greene infusion. It was, could dark matter be ordinary matter with ordinary gravity in a parallel universe? Because for reasons I don't understand the math of, the field theory equations of, you were telling me that electromagnetic energy cannot escape our space-time, but gravity can.
In a certain model called the brane universe, where our universe, B-R-A-N-E, it comes out
as
of
a
string
membrane.
theory. Yeah, it's a membrane. So our universe is like a 4-dimensional membrane floating in a higher dimensional universe that might have other membranes.
Higher dimensional membranes.
Yes, and those other membranes like parallel to us, like 2 slices of bread and a big loaf of bread.
I like it. So, so one slice of bread is some other membranal universe.
Yeah.
Ours is this one, but it's one multi-brane.
Yeah.
Okay, and so gravity could leak out of one into the other.
Or it could just be yeah, that's right. So the gravitational pull. Yeah,
that's what I'm getting.
Yeah.
So if the other universe has 6 times, see, this is where you corrected me. Because I was thinking, because we have 6 times as much force of gravity operating in the universe as matter and energy can account for it.
Okay.
Factor of 6.
Right.
So I was saying, why isn't it just a parallel universe that has 6 times the mass, and it's leakage into our universe, and we're trying to feel the elephant, trying to figure out what it is, but it's just regular matter in another universe whose gravity leaked. But then you said, if it's in another membrane, it's going to be dropping off faster than 1 over r squared.
Yeah.
like 1/r². There's some higher dimension.
Yeah.
And if that's the case, it has to be way more than 6 times.
But you could imagine rigging it so that it would have the right amount.
Yes.
And people have studied this, and it's hard to make these theories work in detail.
And be all
But in
self-consistent.
principle, it's an idea that's absolutely worthy of investigating, because that's one way to make it invisible. Just put it in another
Just
membrane.
stick it somewhere else.
Yeah, exactly.
And then where we can still calculate with it, it's not a problem.
Yeah.
Right.
Yeah.
That's crazy.
Man.
Oh, man.
All right.
I don't know what to believe about anything. Nothing is real. Nothing is real, man.
Dark energy. I'm curious about this because it was a natural arithmetic element of Einstein's equations. It's like an integration constant, as I understood it.
You talk about the cosmological constant?
The cosmological constant in his equations that enabled Lemaitre to calculate that the universe is either expanding or, well, the universe is not static. And so there's a term there. And if you've had calculus, you might remember there's a constant of integration. Often it's just 0 and you can ignore it. But when we were in graduate school, I'm a little older than you, when we were in graduate school, we always recognized, we paid homage to that constant, but said, let's assume it's 0. If this term existed, it would mean there was a force operating in the universe opposite that of gravity.
Depending on the sign of the cosmological constant, but yes. Because it could have either sign.
Okay, it would either work with gravity or against it. Okay,
exactly.
But if we had a static universe, it would be something just holding up the universe against the collapse of gravity.
Which is why Einstein thought of it.
And we didn't have any reason to think it, so it could be 0, and but we always had to go through that portal. We say, here it is, we set it to 0 and move on.
Exactly.
Okay, then it gets discovered.
Yeah.
Okay, dark energy gets discovered in 1998, gets the Nobel Prize, using quantum physics, which has done so well by us, perhaps the most successful theory ever about anything, fails in its attempt to predict the amount of dark energy in the universe.
Yeah.
And it fails badly by a factor.
What's up with that, Brian?
Of a Google.
Wow, by a factor of
bigger than a Google. 10 to like, it's like 10 to 123 or something.
Google is 10 to the 100th?
Yeah.
It gets the wrong answer by the biggest amount ever in a mismatch between theory and observation.
Yeah.
Where are we with the dark energy theorists?
Well, look, what this is showing us is that quantum mechanics is incredibly successful when you apply it to the electromagnetic force, to the weak nuclear force, to the strong nuclear force. But we've long known that when you apply it to gravity, something goes wrong, something changes. This is the motivation for string theory, and this is the motivation for trying to go beyond conventional approaches. And so you're absolutely right. This is the clearest signal that something is wrong. Now, here's, I think, our best guess.
That's not something's wrong. That's actually a good thing.
Well, it's an opportunity.
Yeah.
Opportunity. That's the way.
Yeah, it's a huge opportunity.
Yeah, the press always says, oh, scientists are angry or this. No, we're delighted.
Yeah.
If something breaks, oh my gosh, it's a new thing.
Yeah,
That's
exactly.
right. That's right. And so I would say my guess where we're going is, and many of my colleagues agree with me, that you can't quantize gravity the way you had to quantize Faraday and Maxwell's electromagnetism, or the way it had to quantize the weak or strong nuclear forces. It may be that gravity and quantum mechanics are already so intimately connected that it's a completely different mindset when you approach them. You don't take the rules of quantum mechanics and slap them onto gravity. That gets you the wrong answer. That's the wrong approach. In fact, this idea of entanglement and wormholes suggests that gravity and quantum mechanics, they're already in there. They're already there.
That makes sense.
They already have the shotgun wedding.
Exactly.
You just was in the tent.
Exactly. So you just need to understand that melding better. And when you do, perhaps you'll be able to do a calculation of the cosmological constant and get the right answer.
Right.
Yeah. Now, another answer might be maybe the cosmological constant is not a constant. Right? There's recent
They're
data.
working on that now.
Yeah.
Yeah.
Right. Maybe it's changing over time. And so you don't actually calculate the number. You just need to understand the dynamical process.
However, doesn't the math in general relativity require that it be constant.
No.
That's how it came out of the integral.
There can be a constant, but it doesn't have to be the only contribution that looks like that constant. And the other contribution can change over time.
What do you say there?
It can be a constant,
but
it doesn't have to look like, and then...
No, it's not the only contribution, to that term.
Right.
So you can have a field that slowly varies over time, and that field may dominate this contribution.
Field is meta to that equation.
Yes.
Look at that.
It is meta
God.
to that equation.
Oh my
Absolutely.
gosh.
So Einstein did not talk about that
No, he
field.
didn't. No, he wasn't there
and
yet.
You're right. And he did talk about the constant, because you're right. It's just an integration
It's
constant.
an integration constant.
It's right there.
It's a constant. It's
Yes.
a constant.
Yes.
So if in fact it needs to modify, because that's how they reconcile this tension in the age of the universe.
Yes.
Because the age of the universe, in my day, we didn't know it by a factor of 2. Right. Now people are, there's a 10% difference.
So it's more than 6,000 years. Is what you're saying.
Yes, that's exactly what I'm saying. Yes. When Noah's flood took place. So to relieve the tension, as we describe it, this was a 10%, some single-digit percent. Uncertainty in the age of the universe. Actually, not uncertainty. These two methods have very small, tight uncertainties that do not overlap.
Yeah.
That's why everyone is freaking out. And as I learned recently, you can resolve that by allowing the cosmological constant to vary in some way, but that's a meta variation on top of Einstein.
Yeah, no, this Hubble tension that people are struggling with today is exactly something that also may point toward a dynamical value. So we'll see.
Right.
But yes, the true test of a version of gravity that you fully understand with quantum mechanics included would be a calculation of the cosmological constant and get a number.
Are you and your people smart enough to get this figured out?
I don't think so.
And that's our show. Good answer. Because I've dragged you over the coals
We
about
have come
that.
full circle.
Because I've told him, I said, look, Einstein came up with general relativity in 10 years by himself. You string theorists, there's dozens of you have been working on this for decades. Either you're all wrong or you're all just too stupid to figure it out.
And it's probably a combination of both.
Love you, man. Brian, thanks for coming back.
My pleasure.
To Star
Thank you.
Talk. Always good, Chuck.
So great.
Chuck, we'll find you in the hospital.
Bless you will. I'm completely fried right now. I'm fried.
Just to take us out, let me remind us all, we are in my office at the Hayden Planetarium of the American Museum of Natural History.
The Cosmic Crib.
The Cosmic Crib. And after this conversation we just had, I delight in realizing and celebrating the fact that just a few pounds of organic matter inside of our heads can not only contemplate, but figure out how the universe works. And yes, we still have a long way to go. And we don't even know how long a way to go remains in front of us. But the distance we've come thus far gives us everything that we call civilization. And it's the power of mind over the mysteries of the universe. And that is a product of the eternal curiosity expressed by our species, beginning in childhood, continuing, for some, into adulthood. We call them scientists, those who never lost that childhood curiosity. Brian Greene, of course, among them. So I'd like to just give a shout out to our species for all that has wondered as we looked up at night, all that we have discovered, and all that we have yet to figure out. That is a cosmic perspective. I'm Neil deGrasse Tyson, your personal astrophysicist. Keep looking up.